So as said, I'm Carina. I work at LSA in the UK. So a bit about Loughborough Surface Analysis. We're based in Loughborough, unsurprisingly, which is right where this blue star is, in England. And we are a contract surface analysis lab, specialising in dynamic sims of semiconductors. We are quite loyal to Kamika. We have 5 operational sims machines, a 3F, 2 4Fs, and 2 7F autos, which we use day in, day out, running them 24/7 basically. And then we also have the ability to use different techniques as well. We have in-house an SEM, an EDX, and a white light profilometer, as well as the ability to do XRF, fib sectioning, various other techniques that could be complementary to the sort of analysis that you would like. The company has been running for about 30 years, so there is an awful lot of sims experience in the building. So I'm going to talk a bit about the basics of sims, just to cover all bases. So there are 2 main sort of types of sims: static sims and dynamic sims. They both work the same, with having a primary ion source that comes in and hits the sample, and the sample is then held at a voltage, whether it be positive or negative. And this voltage across the sample creates an electric field which pushes the secondary ions from the sample through the secondary column to whichever form of extraction and detector is present on that machine. So we have time of flight, which works on how long it takes for the secondary electrons to get from the sample all the way to the detector to identify which mass is being analysed. And then with our magnetic sector sims on the right-hand side, it works on electrostatic extraction and magnetic sector. So we filter out based on charge and then based on mass. And that is how we determine which mass unit we are detecting on the detector. A couple of differences between magnetic sector and the nanosims. With nanosims, you select your 7 masses and you have 7 different detectors, and your masses have to all be within several mass units of each other so that they hit the detector correctly. The difference with magnetic sector, or the Kamika IMS 7Fs, is that we alter the magnetic sector settings so that we rotate through different mass units and focus them all onto the same detector. So we, at low mass resolution, about 400 mass units, we can pick elements from indium down to gallium down to silicon, and we are able to do that. We don't have a limit as to how close the elements of interest have to be. So that's just a small difference between 7Fs and your nanosims that some of you may be using. We also have an awful lot more lenses in magnetic sector sims compared to TOF sims. We have 3 lenses in the primary column and an awful lot going around the secondary column and the extraction units. So it takes a lot more knowledge and effort to focus the beam onto the detector than with TOF sims. So a few pros and cons of TOF and dynamic magnetic sector sims. So TOF is really good at imaging. It can have 1 micron up to 500 micron analysis area with detection limits of parts per million, and has really good spatial resolution for imaging. It's commonly used for biological samples, and just imaging. Whereas the magnetic sector SIMS that we primarily use here at LSA has a much higher detection limit, or much lower detection limit, so we can go down to parts per billion range, and our depth profile can go up to 80 microns if it's required. Because of this, the machine has been optimized for this detection limit and for this ability to depth profile. We do lose some of the spatial resolution, so we can go down to about a micron spatial resolution for imaging, but we still get the depth resolution as we go through the profile. So when you're deciding what sort of SIMS you'd like to use, it's really important to know what you're trying to achieve, whether you want imaging, whether you want depth resolution, what sort of concentrations you expect to have in your sample. Okay, so with dynamic SIMS, or magnetic sector SIMS, it's quite important to know what elements you're looking for as you go into the sample. With TOF SIMS, you collect all of the elements simultaneously. With nano SIMS, with magnetic sector SIMS, you have to select the elements you're interested in before you start the profile. And we optimize the conditions that we use for the elements we're interested in. So we have, most SIMS machines have an oxygen beam and a cesium beam. Oxygen is normally ionized to O2 plus and cesium to cesium plus. And with the oxygen beam, we tend to use positive secondary polarity. And the cesium beam, we use negative secondary polarity. And if you want the elements on the right-hand side of this periodic table, we use cesium, and the left-hand side, we use oxygen positive secondaries. But because it's SIMS, there are always a few anomalies that go with that, and some few points we have to take into consideration. So sensitivity to ionization is always the most important for the element of interest. So not the matrix elements, but the doping, the contamination elements that you're interested in. But then we do also have to take into consideration the matrix elements. So metals quite often are influenced by the oxygen content in the sample. So if you use an oxygen primary beam, you negate or reduce the influence of the oxygen content in the sample. But it also roughens a lot more. So if there's aluminium in the sample and we use an oxygen beam, we get a lot more roughening, which can reduce the depth resolution as you go through interfaces. So it's something we have to put into consideration and consider what conditions we're using as we start the analysis. A couple of interesting different points. Silver and gold, you would think that it would be oxygen positives, but they ionize much better under cesium negatives. And it's small little things like that you need to be aware of when you're picking your conditions. Zinc and magnesium, again, they really like ionizing under cesium and positives. So this is a completely different set of conditions, and we're monitoring polyatomics. So we'd monitor the cesium and the magnesium together at mass 157. And then aluminium. Aluminium causes havoc to most analysis that we're running. It really likes ionizing and improves the ability of the surrounding atoms to ionize and increases their number of counts. So we have to, or should take into account, the aluminium content in the material and that influence on the element of interest to ionize. Okay. So magnetic sector SIMS, we can image, but it's not what we're really good at. What we are really good at is depth profiling. So whether that be ion implants, fairly standard boron and silicon, or going down to VCSEL structures. So we can see the resolution being maintained all the way through to 30-40 microns. And we can see the different aluminium content throughout the different layers, which can be really important for semiconductors to make sure that they've got that continuity throughout all of these different layers so that their device will work properly. So ion implants for quantification. We use ion implants with most of our analysis. To be able to quantify data is brilliant. SIMS is a comparative technique. If samples are run on exactly the same day under the same conditions, they can be compared if they are of the same matrix. Using ion implants for quantification means that we can quantify data which can then be compared from day to day, from year to year, which is really good for quality control to make sure the semiconductor being produced is maintaining the integrity that it's needed to create the device to the best quality for the industry. So I'm going to go through a bit about how we use implants to quantify. And this is our raw depth profile from a magnetic sector machine. So we've got intensity on the Y scale and time on the X scale. We can then use two different equations to be able to calculate a relative sensitivity factor. So using equation 2, we can calculate the area under the curve, and having known the ion implants, so when you get an implant made, you know how much of a dose has been put into the sample, and using that and measuring the depth of the crater to put this onto a depth scale, we can get a relative sensitivity factor, which is the sensitivity of the ion of interest compared to the matrix element. And when we add these two equations together, we can then use a known implant to quantify an unknown sample, providing it is of the same matrix. So here we have our process data. So we know this is a 1E15 dose under the curve. And if that area is equal to a 1E15 dose, from that we can work out what the concentration is and what the highest peak concentration is and what our backgrounds are, which is our detection limits. So then if we have an unknown sample with an unknown amount of nitrogen dosed into diamond, having ran this sample under the same conditions as our implant, which has a known dose, we can then use this equation to work out how much nitrogen has been implanted into this sample. And we can quantify it. So from our raw known sample, we can process this into, we have quantified our known sample, and then running an unknown sample under the same conditions, we are then able to process this to work out how much nitrogen has been dosed into the sample. And this can be used and reran, and even under different conditions, the dose should be the same from day to day, which is it's really useful for industry to have numbers on your sample which you can compare continuously. Another thing that we have to be aware of when we are analyzing ion implants is the impact energy. So we are able to change the voltage that we put onto the primary source and the voltage that we put onto the sample. And when doing this, we can work out the impact energy of the prime onto the sample. So working out the primary high voltage minus the sample high voltage divided by the number of atoms in the primary source. So if it's just cesium, there's just one atom or one ion. But with O2 plus, we have to divide it by 2 because you're hitting the sample with a molecular, which reduces the impact energy. So if we use cesium plus 10 kV and a sample high voltage of minus 4.5, we get an impact energy of 14.5 kV. And you can see in the blue line, the profile of the implant that we get at 14.5 kV impact energy. This is the same sample run under different impact energies, and you can see that the profile changes. So the lower the impact energy, the higher the peak, and the sharper the interface as the dose comes down. But what we get when we get a higher peak doesn't mean the amount of dose has changed. It just means the shape of the profile has based on the impact energy. So the area under each of these curves they are all equal. It's just the shape that has changed. So it's really important when you're getting implants measured that you have the same impact energy on each, or you make sure you compare the dose rather than the peak concentration, because these will change depending on impact energy. So if we have really shallow implants, we try and use a low impact energy so we can get this sharp interface and we can see the shape of the peak. But with using lower impact energy, the lower impact energy is a much slower profile. So using 15 kV, this profile would take about 10 minutes, whereas using 6 kV impact energy, the orange profile would probably take 40 to 60 minutes. So if you've got to compromise time over quality of profile, because obviously it costs more to run the machine for a much longer period of time. So contamination that's possible in ion implants. When we get an implant, the first thing we do is rerun a mass spectra. We check which ions or which masses have been implanted into the sample. So this implant was a 130 tellurium implant into indium phosphide. When you get an ion implanted, you pick a specific mass. So all of the dose should be at 130 tellurium. And we can see in this mass spectra, we've got 1E4 counts of 130, and then only about 10 counts of 128 and even less of 122. So this has been a really nice implant. It's clear that we've only got the 130 tellurium. And then when we go on to do a depth profile, this pattern has been shown here, that we have a really nice Gaussian shaped curve for 130 tellurium, minimal for 128, and no implant shape at all in any of the other isotopes. So this implant has been done really nicely. And we can use these equations from earlier to then quantify this and get a peak concentration, which we're then able to use to quantify any tellurium samples in the future. Not just 130, but we can use isotopic ratios to quantify 128 tellurium and all of the other isotopes of tellurium. Yeah. So when we get implants to begin with, they're nice, clean, shiny sample surfaces. And this is our Sims crater. But over time, implants start to degrade and they begin to look like this. So lots of craters going in and out of vacuum, it degrades the sample. We get pock marks on it, and this can degrade the quality of the profile that we get. And if we're using this to quantify data, it could bring inaccuracies into the data. So we wouldn't use this. So what we do is we get ourselves a nice new clean implant, and it begins to look like this. And again, we do the same thing. We run a mass spectra. So this was meant to be a 1:8 implanted into indium phosphide, and our mass spectrum shows peaks for all of the tellurium implants. And this is when we start to bash our heads against the wall. Instead of getting our nice 130 tellurium implant, we get all of the isotopes implanted into the sample. So is the dose that we've been asked to have implanted into this material, is it all at 1:8, or is it separated out of all the different isotopes? So we need to work this out. So we run our depth profile for all of the different isotopes that were present in the mass spec. And we can see that there is an implant shape for all of them. So all of them look Gaussian, and the top of the peak overlays perfectly. This is an indication that when the ion was implanted, there was mass contamination. So the implanter didn't go into high enough resolution to identify the 1:8 tellurium and implant the entire 1E14 dose at 1:8. So we have to take this into account when we're quantifying it. So the 1E14 dose is separated out for all of these isotopes. So the area under each isotope needs to be added up, and that is the 1E14 dose. So in reality, when 1E14 dose should have been implanted, we actually ended up with a 7.86 E13 dose at 1:8 tellurium. And we can then use this to quantify the data. So we've got a like 5E18 peak at 1:8 tellurium, but then we've also got implants at all of the other masses. So it is something we can account for. And it's really important if you're getting implants done that you know whether you've got mass contamination present. Because all of these different masses can contribute to electrical measurements. So you could get discrepancies between your electrical measurements and your SIMS measurements, because we believe if we just run 1:8 tellurium, we will get a different amount of tellurium present, but this would be much lower than your electrical measurements that you would get, because all of the tellurium implants are contributing to this. So when we do much higher mass units, when there's a greater chance of poor mass resolution in the implant, we make sure we monitor multiple isotopes to check that you have got a pure implant. Okay. Just a little question for you, and to have a think about. In both implants, we got a peak at 130.5 AMU. So this wafer should be pure indium phosphide doped with tellurium and beryllium, and the profile was done with cesium negatives. See if you can work out what peak is present at 130.5. Okay. A different type of contamination that we can get in implants is energy contamination. So we can see here, these are selenium implants, both in indium phosphide and gallium arsenide. And we have a lovely Gaussian shape of an implant in the major isotopes of 78 selenium. But then we've also got what look like implants at the lower isotopes, but they've not got the Gaussian shape to them, and the peaks don't overlay. So we know it's not mass contamination. These ones are very sharp peaks, whereas these ones are slightly more curved. And they also don't have, these were run at the same time, they were implanted at the same time, but they don't have the same contamination from the different minor isotopes in each sample, which is also an indication that it's not mass contamination because they will have been implanted under the same conditions. This indication that they don't overlay, or the peaks don't overlay, is indicative of energy contamination. And not much research has actually been done into this, but it's because you get different results depending on which ion implanter you go to. But it's suggested it's because of possible memory effects from the ion implanter. But if anyone wants to do any research into this, it would be a great project to do. But unlike mass contamination, which does affect our measurements, energy contamination doesn't. So this is not part of the dose that went into this 1E15 dose of selenium. We do not need to take these into account when we do the measurement because they are not part of the implant. They are side effects from the ion implantation. But it's nice to know that they're there, and it's a way, it's something that you find out when you prove that there's no mass contamination in an implant. You can then see if there's possible energy contamination. Yeah. Okay. Thank you for listening.